good. Okay. So, as I said, it's the design of the gravel trap is usually carried out by using rules of thumb. I am repeating so it gets recorded. While the design of the sand trap is carried out by using a more detailed procedure. And the reason is that for the gravel trap, we are dealing with a material that is less homogeneous. It's in terms of size, of diameter of the single particles. It's a material that is less uniform, and therefore it's more difficult to describe. In the sand trap, the material is more homogeneous because the gravel trap is operating a kind of a first filter. And also the sand trap is the last step in this process of removal of sediments, so it must be more carefully analyzed. So let's focus on the design of the sand trap, and then I will give you the rules of thumb for the design of the gravel trap. First of all, the sand trap, what is the size? It depends on the shape of the sand trap that you adopt. Usually, according to this scheme, you cannot make it very large if you are working on the side of a river, on the hill slope of a river. And therefore, if you cannot make it very large, it will become quite long. So it's not unusual that you get sand traps that are some 30-40 meters long. The length depends on the transversal dimension of it. So the more you can make it wide, and the shorter it will be. And when I'll describe the procedure for design, you will understand why. So here the target is to design the sand trap in a way that gives enough time to the sediments, to the suspended sediments, to settle down, to reach the floor of the sand trap. So we assume that there is suspended material in the sand trap, and we need to design the residence time of water in there, as I said, to give enough time to sediments to reach the floor of the sand trap. So we are sure that water passing into the upstream tank, which is water flowing above this step that is located on the floor to divide the sand trap from the upstream tank. So water that is flowing above this step, we are sure that it's clean water, at least for the purposes of the downstream uses. As I said, we can allow that some particles, very tiny particles, are conveyed downstream, and the limiting size of the particles that we have to remove depends on the downstream uses. So now let's see how we can design the residence time in the sand trap. First of all, we need to determine what is the time required for a particle to settle down, to reach the floor of the sand trap. So let me go back to the website now. Here we are, and let's move down to the design of the sand trap. And first of all, let me say that this time that is required to the particle to settle down, it's computed by estimating the sedimentation velocity. And the sedimentation velocity is estimated through the Stokes formula, which I think you already demonstrated, proved in other courses. So here there is, if you scroll down, there is the mathematical proof that you can use to derive the Stokes formula. And I'm not going to discuss it in detail. It's based on equating the weight force of the particle with diameter lowercase d with the weight force is equated to the hydrodynamic force, which is, I'm sorry, the resistance that water makes to the particle which is moving downward. I'm sorry again. So if you equate the weight force to the hydrodynamic force, then you obtain the limiting velocity. For increasing velocity of sedimentation, you have an increase of the hydrodynamic force, and therefore there is a velocity such that an equilibrium is reached. And we estimated this velocity Ws with Stokes' formula, which ends up with this final outcome. The velocity of sedimentation Ws is equal to 1 divided 18 me, which multiplies gamma s minus gamma times the d squared. Here you have d is the limiting size of the particle, which we can tolerate downstream. Gamma s is the specific weight of the sediment, and typically it's something like 2500 kilograms per cubic meter. And gamma is the specific weight of water. So gamma s minus gamma is the immersed specific weight of the particle, and me is the dynamic viscosity of water, which is a property of water. You can get the value from tables, you can look on the web. It's a specific property of water which determines the viscosity of the fluid, which in this case is water. So you see that for increasing viscosity, you have a decrease of the velocity of sedimentation. Velocity of sedimentation increases for increasing specific weight of the sediment, and this is of course expected, and velocity also increases for increasing diameter. This is expected as well. You don't need to remember by memory Stokes' formula. You don't need to remember by memory the demonstration. I tell you that sometimes the exam students propose to me to make the demonstration, and I happily accept if it's proposed by you. But I'm not asking that you independently and autonomously study this demonstration. That's fine, even if you want to skip it. I know that you had it in other courses. And also it's not really very relevant to our design, so it's just something that if you need, you can easily study online. Okay, so once that you know the velocity of sedimentation, then let's suppose that you know, because you fixed it, the depth of the sand trap. Usually it's the depth of the sand trap is quite limited because you don't want that to create risk for people, and also you keep the depth limited because you want to minimize the time that is needed for the particle to settle down. And a typical depth is half a meter, 50 centimeters. Usually people don't design deeper sand traps because, as I said, it's not convenient. So if you fixed this depth of 50 centimeters, then you know the time that is required for a particle that is starting from the water surface to reach the ground. This is easy. You divide the 50 centimeters by Ws, by the velocity of sedimentation, and then you get it. Okay, so let's once that you know the residence time, and then I will make a sketch later on the blackboard. Once that you know the residence time, then you can, here you see the formula. T is equal to H, which is the depth, divided by Ws. once that you know the residence time, then basing on the knowledge of the design flow into the sand trap, which is the design flow of your barrage, you know the design flow, then you need to fix the width of the sand trap. And by knowing the depth and the width, you can compute the velocity of the flow into it. So at this stage, let me make a sketch. So 1 second. I need to move this here. Okay, good. Okay, 1 second because I need to get my board. Okay, here we are. Okay. Okay, and now I need to share my screen in this way. Okay. Just 1 second because I'm turning. Okay. And now I need to get today's page. Very good. And then just 1 second because it needs to upload it. It's a bit slow. And while it is uploading, let me see. Still uploading, I don't know for what reason. Give me 1 second. Okay, no problem. I can open a new page because I had the sketch of the sand trap, but it's still not working. Okay, let me try again. Maybe I can make a new page. Okay, let me put a new page here. That's fine. Lecture April 6. Okay, good. And then let me remove this. Okay, very good. Okay, and finally, 1 second. Give me 1 second because I need to. Okay, so let me move forward and then we make the break because I'm still not happy with the screen recorder, but I can't get everything fixed. So as I said, we estimated the WS. Just 1 second, I need to draw it. Okay, we estimated WS, which is okay, and then we fixed H, which may be about 50 centimeters. Okay, of the center up. H is the depth. This is depth. And then we can compute T. T is the time needed by a particle that is located over the water surface to reach the bottom. So if I make a sketch of a sand trap here, and let me see, okay, if I make a sketch of the sediment trap here, and then let's suppose that we have water surface here, okay, this is H, this is H, and let's suppose that we have a sediment particle that is placed again on the surface, and what happens if you have a flow that is going in that direction of the red arrow? It happens that this particle goes down, move forward, and goes down with it takes a time t, and t is equal to, as I said, h divided by ws. Perfect. Now what we need, and this is the purpose actually of our design, what we need is to estimate the length of the sand trap L. Okay, so let's look now at the cross section of the sand trap. This is longitudinal section. Now let's look at the cross section. So the cross section, I can place it up here, and this is our cross section with the water in here. Again, this is H, and again here I have my fluid particle. Now let me indicate with I don't know if I'm using the same letter in the web pages, but I think you can understand. Let's indicate with B the width of the sand trap, and B usually is fixed. So I can write above here that H is already I already gave here. What is B is B is fixed, and it's dictated by how much room you have on the sides of the river. And so if you have enough room, B can be up to tens of meters. It can be 20 meters, 10 meters. In some cases you don't have room enough, and therefore B, the width of the sand trap, could be limited to 2-3 meters. The important thing is that once you fixed H and B, then you can compute the area of the sand trap. Let's suppose that it's a rectangular cross section, and therefore A is simply equal to B times H. Now, at this stage, you know QD. QD is your design flow, correct? Design flow. And you can compute the velocity of the flow in the sand trap. You can compute it because we can write that QD is equal to A times V, where V is the velocity of the flow. And this is a relationship that is known from fluid mechanics. It applies to currents, and therefore it applies to our case. So then you can compute V because you know QD, and if you divide QD times A, V is known. It is convenient that the velocity V is kept quite low, and the reason is that you want to avoid turbulence by all means in the sand trap, because turbulence may move the sediments that settle down. So you absolutely want to avoid this. You want that sediments, once they settle down, they remain there. So you want to avoid turbulence, and for this reason, it's better that V is in the range it's in the range, let's say 0.2, 0.5 meters per second. 0.5 is already maybe too large, okay? Okay, so V is known. Also, it's known T, which is so you know V, and also you know T, which is the residence time, sorry. Okay, so you know these. Now, once that you know V and T, you can compute L, because you have to make sure that L is long enough to give to the water that flows with velocity V the residence time T. And therefore you can compute, let me put it in red, okay, L is equal to, let's see, it's equal to V divided by just 1 second, V times, sorry, T. Okay, let me see. Yes, I think this is correct. So this is your required length. So you want to make sure that it takes time t to the particle that starts from the beginning of the center up and from the water surface. This particle takes a time t to settle down, and it's flowing with velocity v. So you want to make sure that there is enough time for this particle starting from the beginning of the center up and the water surface to settle down. Is this clear? Do you have any question on that? Okay, very good. If you can please take a screenshot of this, because I didn't succeed to put it on the screen recorder. So if you can take a screenshot, this would be perfect. And now let's take 5 minutes break. So I also take the time to set the screen recorder in the proper way. If you have any question, please write on the chat now, and then we can go for the break. Any question? Okay, here I am. Now I have the screen recorder that is recording the page, so it will be in the video. Any questions then? Okay, very good. So now let me get back to the web page, which is here. And that's it for the design of the center up. Some rules of thumb and a summary. First of all, I gave to you a range that is too large for the velocity, and let's take the range that is given here, which is now better specified with a lower value. It's ranging up to 0.115 meters per second. Indeed, in order to avoid turbulence, this is quite delicate. And so now there is also another order of magnitude that can be given by this relationship here. The length of the center up is given by h divided by 0.06. This is a very rough rule of thumb. If you that gives to you a very first order of magnitude. And another thing, I see that there is this relationship here. This is not correct. Sorry, I'm going to correct it soon. So it's not v divided by t, but it's v multiplied by t, the length. And I'm sorry, I noticed even last year that was incorrect, and I forgot to correct it. So I think that's it. And now let me speak about the head tank. The purpose of the head tank, as I said, is to make sure that you have um, always some water above the ceiling of the pipe that brings water downstream, if any. So if you bring water downstream by using a pipe, you need to make sure that the roof of the pipe, let's say, the highest elevation of the pipe entrance is always submerged. And there is a practical rule in order to compute, to design as a first guess, how much should be the water depth above the highest pipe elevation. This should be, so submergence should be at least 1.5 the kinetic term of energy of the current into the pipe. The kinetic term is obtained by the square velocity of square velocity into the pipe. So you have a design velocity into the pipe, you square it and divide by 2g, where g is gravity, and then this is multiplied by 1.5. So this is to make sure that for any working condition of the pipe, you always have enough submergence. Again, this is a rule of thumb which is used for the preliminary design, but it provides a quite accurate estimate. This is a quite accurate estimation, and while the last rule of thumb I gave to you for the length of the sand trap is more approximated. Okay, so now let's talk of the design. Let's talk about the design of the side structures. So what are the side structures? These are the structures that are used, whose purpose is to make sure that the whole structure of the barrage is stable. And here we discuss in particular two things: the foundation, which we will discuss later, and the downstream protection against erosion. We already mentioned very briefly the need to protect from erosion the downstream riverbed. And also we said that our first solution may be to place boulders just downstream the barrage in order to make sure that the riverbed is protected. Boulders are fine. It's a kind of protection that is usually used when there is not a very important flow out of the main spillway. If you are expecting out from the main spillway very turbulent flow with a very relevant amount of discharge, then it's more appropriate that you build something that makes sure, a structure that makes sure that the water flow is accompanied downstream. It's not left to fall, because of course a falling cascade, a falling water flow, it gets even more energy while falling. So in order to avoid this increase of energy, it's better to, and in order to avoid a direct impact of the flow with the riverbed, it may be advisable to accompany downstream the flow with a spillway, and this is a possibility that you see in this figure. So you don't have downstream a vertical wall, downstream the barrage, you don't have a vertical wall, but you put a tilted wall that accompanies the flow downstream. And also you can put in place downstream a pool of water that helps to dissipate the turbulence. And if you look at these type of structures, indeed you see that when the expected flow from the main spillway is important, they protect not just with boulder downstream, but they build structures, structures that are in charge of dissipating the energy. So here the question is, what is the shape to give to this spillway? And the shape is usually determined with lab experiments on small scale models, because as you can understand, to model numerically this very singular type of flow, it's a challenge. It's a challenge because usually you need in numerical modeling to introduce assumptions that basically translate in assuming that the flow is regular with no sudden change of directions and with low turbulence. In a case like this one, instead, the flow is absolutely not regular and you have a lot of turbulence. And for this reason, usually when the barrage is important, these type of spillways are designed through small-scale lab experiments. By doing many of these small-scale lab experiments, people were able in the past to propose an empirical mathematical relationship to describe the shape of this spillway. And the relationship is called, let me see where it's linked, just 1 second. Yeah, here. The relationship is called the Krieger or Shimemi profile. And very often both names are used. People say a profile Krieger / Shimemi. The reason is that these were two famous researchers on fluid mechanics and in particular on hydraulics who proposed this empirical relationship. It was around 1950, and it's an empirical analytical formula which anyway proves to be quite reliable. You don't need to learn it by memory. There is a link here, I am selecting it, that gives to you the relationship. I just want to click on it in order to give you the flavor of that. And it's a page in French, but we just need to look at the analytical relationship, which is given here. You see, I am selecting, okay, and these are the two profiles, the one by Shimemi and the one by Krieger. This is spelled here C-R-A-E, Ger. I think, I'm not sure it is correct. Maybe they use different spelling in different language. I'm used to see C-R-E-A, Ger. Anyway, you see that the two profiles are very similar. There is a small difference in the coefficients. And here it is explained in which conditions they were derived. And also it is explained what is the meaning of the symbols, but it's very clear. Basically, it's an analytical relationship that gives to you this kind of shape. And you see the difference here between the two profiles. It's very small. You see the profile by Krieger. Here it's spelled correctly, by the way, in the figure. And also the profile by Shimemi, which, again, they are very similar. And the purpose here is to avoid any detachment of the flow from the structure. And because, as I said, the detachment is something that we want to avoid, because if you get a flow that is detached by the downstream part of the structure, it's detached from the downstream wall, then the flow creates the void between the flow itself and the structure. And then if for the effect of the external atmospheric pressure, you get that the flow is pushed suddenly against the structure. And so you have a repeated sequence of off, on, off of the flow against the structure, which is damaging the structure itself. And therefore you want to avoid any detachment. Again, you don't need to learn these relationships, absolutely. You just have to know that they exist because they are frequently used also for designing the spillways of dams. A second thing that I want to discuss with you is foundation, and I'm not discussing the foundation in terms of estimating the underneath pressure, the pressure that the structure is making on the soil. I don't want to estimate it because you already know how to compute foundations in terms of vertical forcing, vertical stress on the soil. So we are not repeating it. What I want to talk with you, what I want to discuss with you is piping. I think you may have already discussed piping in other courses like geotechnics, but I just want very briefly mention it to you. What is piping? Piping is infiltration of water under the structure, which originates a water flow under the foundation. And this is very dangerous because piping increases progressively. So if you have some water that is passing by through the structure, then the movement of water progressively enlarges the small canals, underground canals, making them larger. And then they become larger and larger until you have a massive flow below the structure, which provokes the failure of the structure itself. So piping is something that, as I said, we need to absolutely avoid. I just want to mention to you a rule of thumb which is used frequently when designing river barrages. This is the Bleak-Lane relationship. What you have to compute, I go back to the previous figure, what you have to compute is, sorry, the next figure. What you have to compute is the length of the path that water has to follow downstream in order to get from upstream the barrage to downstream of it. And the path can be divided in its horizontal and vertical parts. And you see here in this figure how the vertical part is computed. So it's the sum of the movement of water in downward and upward. And if you have a sheet pile below the foundation, like in this case, you have a quite deep sheet pile upstream and another smaller sheet pile downstream. So if you have sheet piles, you have to compute the vertical path of water by assuming that water first goes downward below the sheet pile and then travels upward to reach the foundation of the structure. So LV1 is the downward path, LV2 is the upward path, and then you have another downward path, LV3, and another upward one, LV4. So the vertical path is the sum of LV1 plus LV2 plus LV3 plus LV4, and the horizontal path is easier, is LH1 plus LH2 plus LH3. And once you compute the horizontal and vertical path, then you can compute here the Bleak-Lane coefficient. You divide the difference in water elevation h between upstream and downstream, so you make the difference between elevation of water upstream and downstream, which is more or less equivalent to the height of the barrage, and then you divide this difference h by the sum of the vertical path plus 1/3 of the horizontal path, and then you get a coefficient f. A coefficient f that is to be compared with values that are given by tables, and you have to make sure that the value given by tables, which depends on soil characteristics below the structure, you have to make sure that the value of f given by table is higher than the ratio that you see on the right hand side. You can find values for the Bleak lane coefficient easily on the web. Again, they depend on the soil type. That's it. And if safety against piping is not ensured, you just have to increase the depth of your sheet piles. And there are several ways. Here you see a figure where sheet piles are what are, first of all, and they can be made by concrete or by iron. And here they are placed not for protecting the barrage, but still they are placed usually to avoid underground flow and to retain usually soil, which usually is wet soil. Okay, I think that's all. Do you have any question on this broad topic? While I am preparing the next one. Okay, so if you don't have any question, my proposal is to move forward with the next lecture, and then I'll propose to you other exercises before the end of the course, but I would say to go with the exercise to Thursday next week. Here you see the web page of our course, and we just talked about design your river barrages. We have these 4 topics that I would like to discuss with you. And be careful, this one, which is scheduled to be the next one, climate change and water resources, it would be the first time that I give this lecture to students of sustainable design of water resource systems. I think it is extremely interesting, and therefore I would like to deliver it now. And I have some premises before delivering that lecture, but I think I can just summarize the premises later. Then what we have left is assessment of human impact on water resources and decision theory and saltwater intrusion. These two, assessment of human impact on water resources and decision theory, I believe they are extremely important, so I want to discuss them with you. So these are lectures that I want to give. Saltwater intrusion is something which is more, less, let's say, less topical for sustainable design of water resource systems. So if we are running out of time, this is something that we could skip. And this is my proposal to you. If you have any comment, and if you have sometimes that something that you don't see here and you really would like to discuss, this is something that we could discuss together. So if you have any proposal now, I think it's clear to you what is left and what we did. So you are in the position of giving suggestions to me, if any. And look, it is not a problem. If you really have something that you think it deserves to be discussed, just let me know. And of course, it's not granted for sure that I can agree. And because, you know, depending on what you propose, it may be not as relevant as other things that I want to discuss, or maybe something I'm not prepared to discuss. And therefore, but this wouldn't be a problem at all. I really would like to get, and I tell you, I never got from students these kind of suggestions, but I really would like to get your view on that. You may have something in mind. You may have had some expectations from this course which were not satisfied. Like some students in the past after the course told me, I would have liked to discuss about design of dams, and I said, look, it's something that we cannot really discuss here because it's a topic that is very broad. It's very requires a lot of time, so I don't think this would be the case. Also, dams are discussed in other courses, but there might be other topics that I am prepared to discuss, and I may be willing to. So, if you have any comment, let me know. And yes, Sam, what? Let me check your question. Just 1 second. And it's here. Can't find it. Just 1 second. It's okay. It's here. Let me see your question. I have a question about the possible exam date. Yes, this is correct. This is correct. You're right. So we can discuss the exam date now. And my premise is that our official closure of the course is in June. And I cannot make any exam before that. So the reason is that we are not allowed to. And even if I make something informal, this is something I'm not allowed to. And we already did the presentations, and the presentation I will make you a proposal for including them in your assessment, but for making the formal exam I have to wait the closure of the lecture, which is let me see the calendar. The closure of the lectures is, I think, it's June 5. Okay, I see. I think it is June 5, which means that I would be willing to make exam starting from June 8. Is this fine to you? And I have no problems in fixing an exam. June 8 is a Monday. Keep in mind that the exam will be online. It may be possible that it's also we are allowed also to make it in physical presence, but I think this is unlikely actually. But in any case, you will have the opportunity to make it online in any case, and therefore just let's keep in mind that it's online, it's an oral examination. So one possibility could be June 8 or 9. The only concern I have for June 8 is that you will have several other exams in that day. So it may be June 8, 9 or 10. It depends on your preference. And then after, I would say a couple of weeks. So it could be, the second one could be June 24. And then there will be a third one in July. So let me see, I don't think I am allowed to put any pool, but I don't know why, but usually. So let me see, option 1, June. I try June 8, option 2, June 9, June 9, option 3, June 10. Let's see. So the question is first exam. I am pretty sure that when I move forward, it doesn't allow me to go. No, I think it's okay. So let's see. I don't understand. No, it doesn't show up. I think you can't see it, correct? It's just forms at the conversation, but let me see what is this. Okay. So let me say, if I say June 10, is it fine to you? Or would you prefer June 8? If you can please write on the chat. I don't see anything. So let me, okay, June 8, okay, let me see, 10, 10, okay. Okay, let's say, I think you are mixed. Okay, let's say June 10, okay? Let me just take a note. 1 second, I need a pen. Okay, so let's say June 10 and June 24. So we keep Wednesday as a date. And if it is, I would say in the morning, and if it is in physical presence, it will be in Via del Risorgimento in Bologna. And yeah, Massimiliano, don't worry. If it's just a problem for you, we can find a way. It can be 1 day earlier or 1 day later. It's no problem. Okay, you just have to let me know, and then it's okay. And as I said, if it will be both in physical presence and online, you may take it in physical presence in Via del Risorgimento, or you may take it online. No problem at all. You decide. Okay. So let me go with again with the web page. So for the exam, I think we are fine. So web page, and so if you agree, I would pass to climate change and water resources. It's a web page that is continuously updated. This topic, which I am discussing now, is quite descriptive. There is nothing to learn in a quantitative way. There are no relationship. It's just something that I want you to know, and I want to discuss with you, because it's becoming more and more relevant for water resources management and for sustainability. So it is indeed a topic, climate change, that is extremely relevant to what we are discussing here. As you know, there is no need that I stress the importance of climate change. Another thing that you know is that unfortunately, and I say really this is unfortunate, it's a controversial topic. It's extremely controversial, and this is unfortunate because really it is detrimental for a profitable discussion, because it's a topic where there is a lot of uncertainty. So when you have a lot of uncertainty, I think that controversy doesn't help, really doesn't help. And also the controversy is not, I mean, it's not discussing what is relevant for engineering. I think that the paradox is that on what is relevant for engineering there is agreement, but it's the way we should get to target that is controversial. So I think there is agreement on the fact that we need to adapt to climate change. So we need to adapt to it, and whatever is your opinion on climate change, whatever is your political orientation, I think there is agreement that we need to adapt on climate change. The controversy is mainly about what is causing it, and therefore there is a controversy that is somehow, I mean, limited on what are the best strategies to get to target. But much of the controversy is related to the political setting. So what is the role that governments should take in order to support mitigation of climate change? So the discussion, as I said, and to make a summary, is not on what we need to do. We need to adapt. This is agreed. The discussion is a little bit on the causes and on the role of politics, and also on the role of scientists, because the role of the scientist is something that is frequently discussed. There is, on the one hand, a strong belief that scientists should not take political decisions. The role of scientists, some people say, should be that of exploring the scientific implication and presenting to decision makers technical support, presenting enough information to support their decision. But then, on the one hand, some people say that scientists should not suggest the best decision to politicians. They should be, in a way, impartial. On the other hand, there is an emerging school of thought that affirms that scientists should also suggest the political decisions. And this is something that it's a bit tricky, because it has an influence on the way you present the results. So some people say, for instance, scientists should not explicitly mention uncertainty when they are talking about climate change, because if you present the reality about uncertainty, then politicians will take different decisions. And therefore, some people say scientists should be more quantitative and should really suggest the way forward. Other people say no, scientists should just present the truth of what they know and should therefore present uncertainty in its full extension, and then the decisions are on the remits of the politicians. It's a bit relevant, and to clarify to you why it's relevant, I give to you an example which is relevant to what we are living. Yesterday I saw on the TV an interview to the Minister of Schools in Italy, Minister of, we call it Minister of Instruction, and a famous medical doctor. He is a virologist. And therefore the commentator asked the minister, do you think we will go back to school, the children will go back to school in May? And she said, I am listening to scientists' opinion, I'm listening for the scientists to tell me what we should do. And the medical doctor replied, look, I will tell you what is the viral situation, what is the risk that you run if you send the children to school. There will be for sure some risk, so I will tell you what the risks are, but I will not tell you whether or not the children have to go to school. This is your decision. And this is extremely important, because, it's not only a matter of responsibility. It's just a matter of what is the role of the scientist or not. Because if the scientist says children can go to school, there is the implication that there is little uncertainty in what they are saying. If the scientists say the risk is 20%, it's a completely different message. And I think this is a relevant example. In climate change is more or less the same thing. Some people say that the scientists should not emphasize uncertainty in climate change studies. Some other people say, no, they should. But of course, the outcome is completely different, because if you present a climatic projection and that's it, it's one story. If you present a climatic projection with uncertainty, it's a completely different story. And then the politicians will take different decisions. So this is why it's very controversial, and it's also controversial because people are very passionate about it, because climate change basically has a direct effect on public health, and some people say that it's undermining our future. So this is why it's a bit controversial. But again, this is very unfortunate, because we are engineers, and first of all we need to take an objective approach. We need to develop a balanced view, a very objective view of our problems. And when a topic is controversial, it's very difficult to get an objective view. So this is also the reason why I want to discuss it with you. So the first part of this lecture just says that climate change is regarded as a major threat to sustainability, and also some people say that it may lead to human extinction. So it's extremely relevant for, especially for scientists and politicians and policymakers. Actually, the public is still not very sensitive on it, but this is something that, of course, it could be discussed. So what is the physics behind climate change? I think you already know it. It's the greenhouse effect, which is causing an increase of temperature, which derives from the increased concentration of greenhouse gases, and one is the CO2, but there are other greenhouse gases. These are produced naturally by vegetation to some extent, and also they are produced naturally by the oceans. The oceans, they can release a lot of greenhouse gases when they are warmed up, and the increased concentration of these greenhouse gases causes a trap of the back radiation from the Earth, a trap of the back radiation into the atmosphere, and this causes an increase of temperature. So the physics is very clear in the big picture. So the big picture again is very clear. There are a lot of similar sketches like this one that you can find in the literature. Increasing temperature of the atmosphere implies several subsequent changes in the hydrological cycle. I mean, the impact of climate change over humans is, for the great majority, governed by the hydrological cycle. The direct impact of raising temperature is limited. It's just the let's call it indirect impact that is relevant through the hydrological cycle, which means heavy storms, which means heavy floods, which means droughts. These are the impacts that indeed are the most relevant. Here you can see a picture of global warming, and it's an animated picture, and therefore you can see the progress of warming from 1960 to today. It's a warming that is subjected to uncertainty in the estimation, but it's a reality, because if you look at glaciers, and you can find many similar pictures like the one that I'm showing here, if you look at glaciers, it's clear that there has been a considerable warming with a pace that I'm going to describe in a few minutes. And keep in mind that I spoke about uncertainty because indeed the amount of global warming is something that is under discussion, and it's a very controversial discussion again, because there is the feeling that the estimation of global warming is influenced by the urban heat island effect. There are a lot of contributions which prove that into the cities the temperature is increased more than outside, and several monitoring stations are located within the area of the urban heat island effect. So the moral of the story is that if you look at the warming of the past 30 years and you look at the ground measurements, you get an average increase, again in the past 30 years, of about 0.6 degrees, which is quite relevant. I mean, 0.6 is relevant. Don't think of in absolute terms. It's something that you cannot individually perceive, but still it's extremely relevant in terms of glacier retreats, as you can see in this picture. So it's indeed huge. On the other hand, if you look at the measurement from the satellites, which refer to the troposphere, the warming is 0.3, so it's half. And this is supporting the feeling that probably the ground measurements are impacted by the urban heat island effect. Also, there are other studies, as I said, which prove that in the cities there is more warming than outside. On the other hand, this is a global average. There are some hotspots, like the Alps, for unknown reasons, have warmed up more than the average. In the Alps, it is estimated that in the past 30 years, the temperature has increased 1 degree, and in some very limited hotspots, maybe even more. For sure, into the cities, the temperature is increased more, but also, as I said, in the Alps, which is something that the reasons are still unknown. So before the break, let's look at this picture. This is a picture. There are several reconstructions of this type, which you can find on the web. The several reconstructions differ a little bit between each other. If you look at this one, which is usually taken as um, um, a pessimist reconstruction, meaning that there are other reconstructions that show less relevant warming. But if we trust this one and we go to 1990, and we refer to the very recent measurement, you see that indeed we passed from an anomaly of 0.3 around 1990 to an anomaly of 0.9, maybe even something more in 2017, which means an increase, as I said, of 0.6, 0.65 degrees. And this reflects what I mentioned to you before. And you see that here I mentioned the anomaly in the Alps. Okay, I think we can stop 15 minutes. Do you have any questions so far? Is perfect. Very good. Okay, now let me go back to climate. It's here. So, as I said, there are other consequences besides global warming of the increase of the concentration of greenhouse gases, because warming in turn induces impacts on the hydrological cycle. The first impact is that according to the Clausius-Clapeyron equation, we expect that the moisture content in the atmosphere increases 6-7% per each degree of warming, which means that given that in the past 30 years we had something that is close to 1 degree of warming, we may expect in the past 30 years an increase of moisture content in the atmosphere of again about 6-7%. Actually, it's the saturation concentration that increases 6-7%. Of course, in order to increase the moisture up to saturation, you have to get enough evaporation. Actually, evaporation is expected to increase under warming for obvious reasons. Still, it's not very clear why there is, according to observations, there has been a decrease in evaporation after warming. And the reason may be that the global warming is changing also the wind field. Evaporation depends on temperature, but also on wind very much, and therefore a change in the wind field may have influenced evaporation. It seems that the wind velocity is decreased on average under warming, and this may be the reason why evaporation is, according to measurement, seems to be not increased. However, if one accepts the assumption that there is more water into the atmosphere, of course, this may lead to an increased severity of rainfall, or let's say to an increased volume of rainfall. This is translated in technical terms by saying that the hydrologic cycle is accelerated. Accelerated because under warming, if you have more, keep in mind the amount of water is always the same in the Earth system. So if you have warming, you have an increased presence of water in the atmosphere, which translates into more rainfall and again more evapotranspiration. So there might be an acceleration. Actually, if you look at the observations, we see that the average rainfall is not increased in several places in the world. Rainfall is measured with, in the long time scale, is measured with accuracy. And it looks like average rainfall is not, as I said, not changed, but it might be changed, the intensity of rainfall. Because if you have less events with less and more intensive events, then you can preserve the mean with fewer events with higher intensity, or you may preserve the mean with more frequent events with lower intensity. So it is the complex, it is the integration of frequency and intensity that may have been changed by anyway keeping the mean unchanged. And therefore the interpretation, the dominant interpretation, is that we are getting less rainy days with higher intensity. And less rainy days may mean that we have more droughts. So the interpretation is that, given that the mean is not changed, we may have had more floods and more droughts. And if you combine the two, the average of water resources remains the same, but you have more extremes. And this is a potential consequence of global warming. And also there are other changes that have been induced, like changes in sea level, which leads to changes in saltwater intrusion, and other changes in cascade. There are also some societal impacts that were caused by global warming, which translates in increasing water demand, which in turn provides a feedback. Look, the purpose of this lecture is, at the end of the story, to show to you that if you look at the observations, it looks like the changes have taken place, but they are not extremely relevant. And therefore, catastrophic predictions may seem a little bit exaggerated. But there is an important consideration to make, and the consideration is that we cannot say that the changes that occurred under 1 degree of warming in the past 30 years will have the same order of magnitude for the next 1 degree of warming, because the system is non-linear. So if we change it from one state to another state, which is today's state, through 1 degree of warming, We cannot say that the next degree, I'm saying again, we will have the same changes. Because again, the system is non-linear. The consideration is written here. If there is a tipping point, which is typical of non-linear systems, remember, a linear system means that you can apply the superimposition principle. A linear system means that 1 degree of change in the past will have the same consequences as 1 degree of change in the future. This is linearity. But non-linear systems may be characterized by threshold effects or tipping points. What is a tipping point? It is defined as a point when a system changes from one given stable state to another stable state in a manner that after we passed the tipping point, we cannot come back, we cannot go back to the previous state. So the tipping point is the limit, is the boundary between two stable states. And then when you shift from one stable state to the other, to go back may be impossible or very tough, very hard. In ecology, there are several examples of processes that lead to tipping points. So, for the same climatic conditions, for instance, you may have two very different vegetation types. And to shift from one type to the other one, it may happen because there are some variables that pass a tipping point. And then when you get in the other state, it's stable as well. And to go back may be, as I said, very hard or impossible. So some researchers postulate that also the climate system may have tipping points, which, for instance, I give you an example. There are some researchers who postulate that beneath, in the underground of Greenland, there are considerable masses of liquid water. And the reason why it's liquid is that when you go deep into the ice, the increasing pressure lowers the limiting temperature for icing, which is not anymore 0, but it's below 0. And when you go deep, of course, there is an increased warming, which comes from the Earth's surface, the Earth's nucleus. And therefore, some people postulate that in the underground, and actually they are making prospections now, to estimate the size of these inner lakes. These inner lakes were discovered relatively recently. It's something that was discovered the underground lakes in Greenland were discovered, I think, no more than 20 years ago. And now they are trying to estimate the volume of these lakes. So they postulate that if we have decrease of the thickness of the ice at the surface, it may suddenly break, and this huge amounts of underground liquid water may be released into the ocean suddenly, in a way that, of course, this is a tipping point, and in a way that we cannot go back to the previous state because we are underwarming. So once that you get some ice that is melt, and therefore the thickness is reduced, you cannot reconstruct it under warming. And therefore this may lead to a sudden increase of sea level. And this is why people are concerned by sea level increase, even if so far the sea level increase, as we will see, has not been so much relevant under warming. So you see that there are several uncertainties in our knowledge of the climate system, and the Earth system in general. And this is a key principle that I want you to be aware of. So there is a lot of uncertainty in our comprehension of the climate system and the Earth system. And one very meaningful example is what I just said. Our knowledge of the internal behavior of Greenland, our knowledge of tipping points, potential tipping points. They may exist or may not exist, but if we ignore them, we could suddenly change from a stable state to another stable state, which undermines our capability to go back. So this is why some scientists are convinced that we are already too late in mitigating the human impact on climate change. On the other hand, again, there is uncertainty, and therefore the role of the scientist is particularly delicate, as I said at the beginning. It's particularly delicate because, as I am stating here, these potential irreversible impacts are capturing the attention of the global public and therefore of politicians and policymakers. And there were several global forums like COP that were activated to discuss the problem. And there are several of them. I think there is a question by Maurus. I think it would be nice if you stepped in with the micro and asked him, or if you prefer the chat, as you want.
No, I didn't want to interrupt you. That's why I just wrote in there, and I thought you're gonna tell me when it suits you.
Okay.
So if you want, you can also finish that paragraph.
Okay, I finished the paragraph. And so there were a lot of forums that were, as I said, organized, which are still ongoing. And also there has been recently an increased attention for the action of the youth movement, who basically pointed out the importance, the societal importance of the topic. We already knew that it was societally important, but indeed, in the past few years, there has been an increasing pressure due to the fact that some scientists postulated that by 2030 we urgently need to put in place some effective actions. There are, of course, in some cases, excess of alarmisms, and there are some links that I posted in the web page. Let's see if they are still working or not. And some people said recently that 2020 is a deadline to avert climate catastrophe. You can find many of these links, and also here is another one. This is quite old, it's 2017, and it was stated that the world has 3 years left to stop dangerous climate change. I think these are excessive. These are too much. On the other hand, there is the feeling that if you don't exaggerate, people don't get it. And this is another element that is strongly discussed. Also, it is discussed during these days about the pandemic. There are some medical doctors who ask the politician not to be optimistic because they want people staying at home. On the other hand, the politicians say, yes, but I also need to give some positive feeling to people, otherwise they get mad. It's a difficult debate. And for climate change is very relevant. I mean, on the one hand, there are indeed scientists who are very convinced that they have to be very catastrophic, otherwise they don't get the attention of the public. On the other hand, there are other scientists who say, look, if you claim that there is the story of the wolf. If you say wolf, wolf, wolf many times, then of course you get the opposite result, that people don't care about your alarms. So, I mean, it's indeed a difficult discussion, and I would say it's also very interesting. It's very interesting for an engineer because the engineer has a fundamental role here. And before giving the word to Maurus, I want to say a couple of few things more. And first of all, why is the role of the engineer relevant? Look, this is also debated because there are some scientists who think that the engineer doesn't have any role in that, because engineering, when comes into play, it comes into play when you want to adapt to climate change, and adaptation is refused by some people, because adaptation means, okay, I got it, and then I have to deal with it. these people who are against adaptation, they are for mitigation. They say we shouldn't adapt, we should mitigate, which is completely different. Adaptation is where engineers come in, but mitigation is not for engineers. Mitigation is only marginally for engineers. It's for climate scientists, which have to study the climate system and determine what is the amount of reduction of CO2 that we have to attain. And of course, then you can call engineers into play to design carbon capture, for instance, or to design industries with low impact. But the main core of the business is not the correct term. The main core of the problem, of the scientific problem, is not for engineers. While the core of adaptation is for engineers indeed, because once that you get less water, once that you get too much water, too many floods, it's the engineer that has to devise this. So I think that for engineers, this debate is extremely important. And this is also a scientific controversy. And I mean, I think it is unfortunate, but on the other hand, it's not the first time. Here there is a paragraph where I show that the history of science is characterized by several controversies, and they are extremely interesting to know and to study. And I think it is extremely interesting to look at history, but be careful because, you know, the climate debate is very controversial. And if you make reference to the history, you may be criticized because some people may say that the current problem is something that is unprecedented because it's global. So if you mention Galileo, and it's another very nice example of a historical controversy, you may get criticized. Okay, so before I go to the quantitative part of this lecture, I would like Maurus at this stage to give the word to you, please, and other questions.
Thanks. I just wanted to ask, I have two questions basically. And the first one is there a prediction on the potential alternative stable state which could be reached after the tipping point?
Okay, yes, there are several climate studies which examined several different types of tipping points. There are several studies in ecology which demonstrate what could be another stable state for the Amazon forest, for instance. If you continue cutting trees, it may become a savanna because it has been demonstrated that it's another stable state. And there are also other studies which prove what could be another stable state with no ice caps. And in principle, this is not impossible. I think the history of Earth already passed periods without ice caps. But of course, the problem here is also the societal development, which is unprecedented, and the velocity of these events. Because if changes occurs in a very long time, there is time to adapt, and therefore no problem. I mean, we already had massive changes in the past of the climate, but the problem is that today it seems to be faster. So if you get a fast change of the climate, you don't have time to adapt, and therefore you get wars and international tensions, you get migration, etc. But there are several studies. The problem with these studies is uncertainty. I will discuss about uncertainty later. So, I mean, we cannot say anything for sure, and this is the problem. Otherwise, we wouldn't have this debate. You had another question?
Yes, thanks. The second question is, if I assume that there is a tipping point, doesn't that to some extent mean that all the predictions that we have at the moment are somewhat more or less useless because we say they will reach one point from which I don't know in which state it will suddenly migrate?
You know, I think the usefulness of a prediction is related to its uncertainty. And let me say some more. it's related to the uncertainty of the uncertainty. It seems like a game of words, but if you make a prediction and you were able to estimate uncertainty in a way that is reliable, I think this is anyway a very useful prediction. So if we could have a prediction like, okay, if you assume that there is no tipping point, this is my prediction. If you, the tipping point is likely or not, if we were able to say that there is an alternative scenario with 10% probability, I think this would be perfect. This is what we are used to do in engineering. The problem is that the estimates of uncertainty, it's not reliable, and this is the big problem. And therefore, to reply to your question, I think indeed there are some scientists who say that that the prediction of climate, the predictions that we have now are not that useful, because they are depicting something that whose reliability we cannot quantify. On the other hand, people who strongly believe in the activity of IPCC, they say that all the models that IPCC used are in a way in agreement, and therefore the fact that there is agreement means that these predictions are credible. So I'm not sure I replied in a satisfactory way to your question, but the problem is precisely what I said. So it's the fact that we are not really sure of uncertainty of climate predictions. Other questions?
Got it. Thank you.
And keep in mind, you have to be critical also with what I say, because keep in mind that there is a widespread belief that engineers are more or less skeptics. And you know that there is this categorization of climate scientists between skeptics and I don't know how to call them, but let's say the other ones, IPCC, and some say skeptics and orthodoxies. So there is the belief that skeptics is a species that is extincted, but actually, if you look on the web, it's not like that. I cannot say how many scientists are skeptics and how many are not. Also because there is no definition for what skeptic means. Because I think there is no climate scientist that is convinced that humans are not influential on climate. So there is no one, I would say. So if you take this definition of climate skeptic, if a skeptic is one that neglects the human influence on climate, I would say that 100% of the scientists are not skeptics. But if you define skeptics as people who are not convinced on the reliability of climate models, then you get a lot of skeptics. So it depends on how you define that. And engineers and the geologists are in a way frequently defined as close to skeptics. So, I mean, you have to be very critical also in my respect. Okay, because you will find other scientists who will tell you that climate models are reliable, completely reliable. As an engineer, I have to say that when I put a signature on a design, I take the responsibility for it. And therefore, it's my duty to assess uncertainty. And before putting a signature, I mean, I am a bit reluctant to say that something is not uncertain if I am not convinced. And this is also, in my opinion, the reason why climate scientists sometimes want to work with engineers, because they want the engineer to put the signature. And you know, if you put a signature, you can be called in front of the court an engineer, something that a climate scientist is not used to. And I want to make another example. You know the history of the L'Aquila earthquake. So there were some scientists that were brought in front of the court because they told people to go back to their home a few hours before the earthquake. And the international community was called it a scandal. They were really, really, I mean, amazed by that, saying that you cannot bring a scientist in front of the court. And when I was called to discuss this, because I am from Italy, so some people at the international level asked me, how could you do that? And I said, look, I am an engineer, so I don't find anything wrong if you make a mistake to be brought in front of the court, because for an engineer it's quite normal. Every time I put a signature on something, I know that if I make a mistake, I am brought in front of the court. And then they said, yes, but if you accept this, then scientists stop working. And I said, why? Why is that? Because if you are a scientist, you have to take responsibility of what you say. And and if you cannot take the responsibility, just say that. So I don't have an opinion on the L'Aquila case because I don't know the details. But in general, I don't refuse the fact that scientists have to take responsibility when they make a prediction. And therefore, as an engineer, I'm very used to that. Okay, so how can we assess uncertainty of climate prediction? There are several different approaches. And usually engineers look at the data. So they try basically to adopt the approach that I explained to you for calibrating hydrological models. They try to compare model results with observations. This is the approach of the engineer. A climate scientist usually doesn't like this kind of approach because it's not easy to find observations for comparison with climate models, and therefore what they tend to do is compare models each other. Now let's discuss the first approach, the approach of the engineer. Look at the data, and therefore I started with this section here, natural variability of climate, because this is something that is very often called into play. So what is natural and what is anthropogenic? And I think this is essential to understand the reliability of climate models, because I want to understand if climate models can reproduce this natural variability. So here there is a section dedicated to the natural variability of climate, which I think it is useful as a term of comparison. And there are several studies on that, several. It's a very rich literature. And there is something that we know very well. We all know about glaciations, okay, which are a relevant example of climate variability. And keep in mind that these glaciations, the reasons why they occurred, is still largely unknown. And if you look at these links, there is Wikipedia links. There is a list of possible explanations. They may have been caused by volcanic eruptions. They may have been caused by changes in the orbit of the Earth, changes in the inclination of the Earth axis. If there is a change by a small amount, very small, of the orientation of the Earth axis, you may get relevant climate changes. And these changes in the orientation may have been caused, for instance, by the impact of meteorites or changes in the magnetic field, something like that. These are all possible causes. We are currently in the tail of the Quaternary glaciation, known in popular terminology as the Ice Age. So we are in the tail of the Ice Age. And here you see the timing of the major glaciations, starting from about 500 millions of years ago. And here you see in the vertical axis the concentration of isotopes as it was retrieved in ice carrots. And by looking at the change in this concentration of isotopes, we can relate these changes to changes in temperature. So you see that there is very relevant fluctuations. There are very relevant fluctuations, and also you may find on the web the reconstructions in terms of temperature. And there were temperature changes during glaciation that are, of course, much more relevant than the current changes. If you think that that the glaciers got very close to the Padana Plain during the last glaciation, you can understand that the changes in temperature have been very relevant. But again, here the question is, how long did it take to these changes to occur? And here you can see a reconstruction of temperature up to 2000 years ago, up to the year 0. And this, of course, doesn't show any trace, any remain of the last glaciation. But you can still see that that in the Middle Age there was the medieval warm period. There is a Wikipedia page describing it, which is consistently reproduced by all the reconstructions, which induced climatic conditions that were even warmer than today's conditions. In particular, the changes that have been observed and witnessed in vegetation, given that it was a long period of warming, are relevant. So it is believed that woods in the Alps extended much higher than today, which means that the temperature was significantly warmer. That period was followed by what is called the Little Ice Age, which terminated around 1750. And after 1750, there has been a steady increase of temperature with a sharp increase in the past 30 years. This reconstruction is something that is a bit controversial. I explain you why. Because the way we retrieve past observations is through these proxy data, which are the expression of an average. I am closing in a couple of minutes. They are the expression of an average, while in the last data that have been put there in the past 30 years are retrieved from ground measurements, which are an expression of the actual temperature. They are in some way averaged in order to get the global view, the global temperature. But it's a simple average of ground data, while when you use proxies, they are expected to give an average reconstruction over a longer period. And this is why some people motivate the fact that in the medieval warm period, it was very long, and therefore the vegetation had time to adapt and to reach higher levels than today. The Little Ice Age is something that we know quite well. There are observations in the literature of glaciers in the Apennines in places where now there is hardly snow in winter. And then this increase of temperature is something that occurred in part for natural causes, because it started around 1750, as I said, and therefore there is probably a mix for the recent time of human impact and natural causes leading to warming, and these natural causes are not known. So there is no explanation for the medieval warm period. There is no explanation for the natural part of the recent warming. If you look at the period 1750, 1850, there was already a warming which is not explained. Okay, I think we can stop here. This part which I'm selecting, I want to explain to you next week. Okay, so just to make a summary, I am available on Thursday for optionally for your questions. You don't lose anything on Thursday if you don't join. I will be available at 10 for at least 1 hour. So again, this is fully optional. Do you have any question to close this lecture?
I have one.
Yes, please.
Or maybe just a suggestion, because I didn't look at your complete script, but I would be interested if you could give us not just Wikipedia articles or so, but on this topic, if you could give us some links to some scientific papers or books or so, where we can see a bit more of the whole debate, not just the rather unreliable Wikipedia articles.
Yeah, I get it. I can tell you
I mean,
that,
if you have something.
yeah, okay. In terms of books, I think there are no suggestions because it's something that is very evolving, and then you know, books is difficult. If we refer to scientific papers, you know, the problem is that there is plenty of literature. It's really very extended. I could make a selection, but actually any selection is a bit problematic, is a bit subjective. And let me say that I don't fully agree that Wikipedia articles are unreliable because they are open for editing by everybody, and I found that in general they are quite balanced. If you look at individual papers, there is much more bias. So I can give you, if you want, two counterexamples. And I can tell you, let me think of counterexamples. Yeah, I have in mind a paper that is under discussion on a journal. I give you a link, and you may see there an example of a skeptic view. Okay, and then I have to think of something that is completely at the opposite side. I think it is interesting if I give you two examples, the two extremes for the hydrological cycle. And one extreme is clear to me because it was just published. I have it in mind. So let me just give you the, I think I can go here. So let me check in this screen, hydrological, hydrology. And so this journal, which I'm now pointing you to, this is open access. It's one of the most known international journals of hydrology, and I would say that I think it is the top one now in terms of impact factor, but I don't really rely much on the impact factor. In any case, it has the nice feature that is open. And if you search for, this journal works in this way. There is an open discussion, so the paper is published before review, and the review is open. The review is done by nominating peers who are obliged to comment on the paper, and the commenting is done online, and then any people can submit comments. The difference between the reviewers and the other comments is that the reviewers can choose to be anonymous, while the other people who comment have to reveal their identity. So it's interesting to look at the discussion papers, and let me see, recent papers. Let me see if I can see. They changed the website, so I'm trying to get oriented where the discussion papers are. So let me see, hydrology and earth system sciences discussions. Let me look at it. Okay, here it is. So here are the discussion papers. And let me see if I can find, these are the papers under discussion. Let me see if I can, okay, this is what I meant. Revisiting global hydrological cycle, is it intensifying? I'm posting the link on the chat, 1 second. The chat is here. So here you get the link and you can have a look. And just a few words, this person here, Dimitris Koutsayanis, is a well-known scientist, quite well established with several awards. It's known to be a skeptic, and he's a person with whom I worked a lot. So, I mean, I can say that I agree, he's skeptic. On the other hand, he's very well prepared. So this is a paper that I suggest you to read. And then I have to find another example of a completely opposite view. Because in this paper, if you read it, I think it is easy to read. It is interesting because he uses open data to make his analysis. And I think it is interesting because the language is also quite simple. But it is biased, and I have to give to you the opposite view. And if you asked me, give me an article that is unbiased, I cannot really help you, because the literature is so extended that judging what is biased and what is unbiased, it's very, very personal. And for instance, if you ask this person, Dimitris Koutsayanis, whether this paper is biased, he would say no, because it's based on data. So he's showing the data, and it's open data, so you can check. So he would say, if you think I am biased, just check and remake my graphics, because it's everything is available. He would say that he's not unbiased, but of course, I mean, I admit that it's an extreme view. So I hope that I could help you. But again, I want to say that Wikipedia, don't say it's unreliable. This is, I don't think it is really, I mean, especially in English, there are so many people that are editing the articles. And if you look at the discussion behind an article, you can get an overview of how long it has been discussed. And if you look at the Wikipedia links on climate change, they have been discussed a lot. Any other question? Okay, so thank you very much. And again, if we don't see virtually each other on Thursday, please get my best wishes for the Easter break, and try to, as I said, to leave it as a break, not as a, I mean, as a negative situation. Thank you very much. Bye. Ciao.